So now we're going to look at an example of how we can use a Taylor series to represent a function that is not a polynomial. In this case, we're going to look at the trig function sine. And our goal is to construct a polynomial that matches the behavior of sine of x and its derivatives at x equals 0. And the idea here then is that we'll be able to use this polynomial to approximate sine at values close to 0. Since we want our polynomial to match the behavior of sine and its derivatives, we'll start by taking derivatives of sine. And we'll see pretty quickly here that there's going to be a pattern, and this pattern is going to allow us to write an infinite polynomial that is going to match the behavior. This is not always going to be the case. We won't always be able to write an infinite polynomial, but in this case we will, because the fourth derivative here is sine, so it's going to repeat. Once we've done that, since we want to match the behavior at x equals 0, what we're going to do is we're going to evaluate sine of x at 0 and all of its derivatives at 0. So the sine of 0 is 0, the first derivative at 0 is going to be 1, the second derivative at 0 is going to be 0, third derivative at 0 is going to be negative 1, and just like the derivatives, we're going to run into a pattern here where it's going to go 0, 1, 0, negative 1, 0, 1, 0, negative 1, and so on. This pattern is going to be really useful because it's going to allow us to write a general term for our polynomial. Now that we've evaluated the derivative of sine at 0 and all of the higher order derivatives at 0, now we can use this formula here and plug those higher order derivatives in for different values. Starting with the value of the function itself at 0, we plug 0 in for k into this formula, and what we end up with is 0 over 0 factorial times x to the 0. It does seem that we have an indeterminate form here, but remember the definition of 0 factorial is 1, so we don't have any trouble. This is just going to be a 0 term. The second term is going to be 1 over 1 factorial times x to the first, so that's just going to be x. The next term we write out, and it ends up being 0 since it's 0 times something. The next term is going to be negative 1 over 3 factorial times x cubed, which would be negative x cubed over 3 factorial. And all of these 0 terms are going to drop out, and we can continue this process over and over again. We do start to see a pattern here, though. We can see that every other term is going to be a 0 term, but every other term is going to be an odd power. So we have x to the first, x to the third, x to the fifth, x to the seventh, and so on. We can also see that every other term is, or each of those terms is being divided by that odd power factorial. So the x to the third term is being divided by 3 factorial, the x to the fifth term is being divided by 5 factorial, and so on. And also we see that it is an alternating series. So we have a positive term here, a negative term here, a positive here, and a negative here, and so on. So we can combine this and write out a polynomial. We can write the first 5 terms of the polynomial here, or at least the first 5 non-zero terms. But we can also use this pattern to write a general term. And this general term would be useful if we were going to try to write this in sigma notation. We could just write this general term with our sigma, starting with n equals 0 and going to infinity. If we would graph this polynomial and compare it to the graph of sine of x, we would see that as we add more and more and more terms into our graph, into the polynomial, we're going to get a more and more accurate representation of the graph of sine of x. It actually turns out that this series converges for all values of sine, or all values of x for the sine curve. So we could even evaluate the sine of, say, 100 with this representation. The only problem is we would have to go out far enough and get enough terms so that it would converge for x equals 100, or at least be a close approximation. Just like any polynomial, in the end, as x approaches infinity or x approaches negative infinity, we're going to get an infinite value, either positive or negative. So it's important to keep in mind that the idea of convergence for something like this is an infinite process. If we cut it off at any point, we're going to have just a regular polynomial which would diverge in the end.